You know, at its core, machine learning is really all about one thing, finding patterns. But what happens when those patterns aren't just simple straight lines? Well, today, we're diving into kernel methods. It's this super elegant way to teach computers to see the world from a completely new perspective, and in doing so, reveal patterns that were hidden in plain sight the whole time.
And that is no exaggeration. This quote from our source material really sets the stage for everything we're about to talk about. I mean, from ancient astronomers charting the stars to modern data scientists, we humans have always been pattern seekers. It's literally what drives discovery.
Just think about Johannes Kepler. For centuries, people just knew the planets moved in perfect circles. It seemed obvious, but Kepler, by sifting through piles and piles of observational data, found the real pattern. It wasn't a circle at all. It was an ellipse, a nonlinear path. He found this hidden relationship simply by looking at the data in a new way, long before computers were around to help.
And that brings us to the core problem we face. Because when we finally did build computers to help us find these patterns, we bumped right into a fundamental issue. Computers, by their very nature, love to think in straight lines.
The first wave of algorithms, things like the perceptron, were absolutely revolutionary for their time. You could throw a big mess of data at them, and they were brilliant at finding the best possible straight line to separate one group from another. It was a fantastic start, but as Kepler showed us, the universe doesn't always play by straight-line rules. And here, you can see the problem crystal clear. On the left, super easy. A straight line does the job perfectly. But the data on the right, well, that's our Kepler problem all over again, but for a machine. There is no way you can draw a single straight line to separate those inner points from the outer ring. Simple linear methods just completely fail. This was the million-dollar question for researchers. If your only tool is a straight ruler, how on earth do you measure a curve? Do you try to invent some incredibly complicated, curvy new ruler? Or is there a smarter way? And it turns out there is a much more elegant way. And it all comes down to a simple change in perspective. This is really the big aha moment. Instead of trying to force a linear tool to solve a nonlinear problem, the big idea was to transform the problem itself into something that a linear tool could solve. Okay, let's go back to that hard problem. We've got our data points laid out on a flat, two-dimensional sheet of paper. The points in the middle belong to one group, and the points forming that outer ring belong to another. And we just can't slice them apart with one straight cut.
But now, what if we could just change our view? Imagine we apply a mathematical function that lifts the points in that center circle upwards, making them higher than the points on the outer ring. We haven't changed the data itself, we're just looking at it from a different angle.
And just like that, from this new vantage point in 3 dimensions, the problem becomes, well, it's kind of trivial. The inner points are now floating above the outer ones, so all we have to do is slide a flat sheet of paper, our simple linear separator, right in between them. That complex circular pattern just became a simple linear one. And this almost magical higher dimensional place has a name. It's called the feature space. It's this sort of constructed reality where we send our data so that its hidden patterns suddenly become obvious and easy to spot. Now, this all leads to a very critical question. You might be sitting there thinking, okay, this sounds incredible, but it also sounds ridiculously complicated and computationally expensive. And you would be absolutely right to ask that. I mean, if we have to actually calculate the new 3D or 100D or maybe even infinite dimensional coordinates for every single data point we have, isn't that just a computational nightmare?
Oh, for sure. In fact, for a lot of interesting problems, it's not just slow, it's literally impossible to compute. And this is where the real genius of the whole method comes into play. It's something called the kernel trick.
So here's the key thing to get. A kernel function is a shortcut. It turns out that most of our linear algorithms don't actually need the exact coordinates of every point in that fancy high-dimensional space. They just need to know the relationship or the similarity between pairs of points. A kernel is a special function that calculates this similarity value directly, as if the points were in that higher space without ever doing the heavy lifting of moving them. It's like knowing the distance between 2 mountain peaks without ever having to actually climb them.
So in practice, the workflow is just beautiful in its simplicity. First, you choose a kernel function. Think of it as picking the right mathematical lens to view your data. Then, you plug that into a standard, efficient, linear algorithm, like a support vector machine. And boom,
That simple algorithm, supercharged by the kernel, can now find an incredibly complex, nonlinear pattern in your original data.
And the impact of this one simple idea is really hard to overstate. This isn't just one cool algorithm, it's like a master key that unlocks a whole family of powerful tools.
See, what kernel methods give us is this unified, principled way to take simple, well-understood linear algorithms and make them massively more powerful. It lets them tackle all sorts of gnarly, nonlinear problems across tons of different fields.
And the applications are just everywhere. You see it in support vector machines, which are absolute powerhouses for classification. You find it in principal component analysis for making complex data simpler. It's used to find patterns in gene sequences, to understand how similar two documents are, and to power image recognition and financial models. I mean, the reach is just immense.
And as our source material points out, this incredible flexibility is really what makes the whole technique so powerful. You can design a kernel for almost any kind of data you can think of: text, images, even complex biological structures. And you can immediately plug it into this whole suite of battle-tested algorithms.
So I guess the big takeaway here is that sometimes the most complex problems don't actually need more complex tools. They just need a new perspective. And it really makes you wonder, doesn't it? What other huge, seemingly unsolvable problems in our world are just a change of perspective away from a simple, elegant solution?